All right, so thank you guys for getting back in here quickly. Sorry for the short break, but this is going to take us into lunch. So after the panel, we're gonna start our lunch. But I'm gonna have Ryan Layer from the University of Colorado over here. He's gonna be moderating the panel today. He's going to do a quick introduction for the speakers, and then we'll invite the first one up and go ahead and get started with the presentations.
All right, thanks. Yeah, so Rick Anderson from Rutgers, Nathaniel Hudson from Illinois Tech, Puyan Jamshidi from University of South Carolina, and Freda Fund from NYU.
All right, thank you. All right, okay, I'm Rick Anderson. I'm with Rutgers University, and my main role is Director of Emerging Technologies for University Online Education Services. And I do all of the taking the new stuff and mashing it with what we can do with faculty and what we can do with students. But I'm also co-founder of Fair Use Building Research Labs, which is a makerspace in New Jersey, one of the first. And then I'm also co-founder of Garden State Combat Robotics League, which is like the second largest robot competition, at least on the East Coast, if not the country. So I do all these really fun things with like 4-H STEM, lifelong learning, all of these different elements kind of cross the thing. So my project crossed these spaces. So I'm really interested in taking like embodied robotics and using like open source curriculums to, sort of what I did with autonomous RC cars a few years ago with Chia Edge, to what I'm doing right now with this concept of embodied robotics. So I started off with Chia racers, so traditional supervised edge and autonomous style, supervised controls. So basically camera, steering angle, Raspberry Pi, teensy microcontroller, custom PCBs, and we set that up as request a Chia racer on Chia Edge. And it works great. It's really fun. And I think that was a really great start, but it was very traditional. And I took that out to like Bergen Tech high school kids, adult like STEM teaching at Center for Math, Science, and Computer Education. And then I take that to my AI study groups, robot build nights. So many things have changed with all these groups that I've been sharing it with. So I've moved on to coachable robots. So this is like taking the idea that I've got a whole mess of robots and I need to control that fleet, but when I need to teach, I need to have the right robot and the right thing all ready to go. So I've been looking at the Robot project with the robot arms, and I have a TalkBot, which is basically an Alexa clone, DIY open source style, full benchmarks, so that you can sort of know what is the pipeline like, and can you fit it on a Pi, and what do you have to do with it. And so with this change, I'm using Chameleon as the control node for the fleet of bots, as well as like the inference hosting, and also the training. So what's going on now is I've got Pis enrolled at Chia Edge. So my ARM container, I can request it, get on there, I can see what the robot arm is doing, take all the data, and basically do the leader and follower calibration and have an operational robot arm. It uses like video 1 and 2, various profiles. So essentially all these have to be registered on Chia Edge. And there's a couple of bumps in the road, but it's actually working pretty well. The other part is teleoperation is another thing, is like using Xbox keyboards, Joy-Cons, really important to create more than just like a leader-follower scenario with like a matching arm, is that there's so many ways to do the controls, and that's a whole like lesson in itself. And the other is to hook simulation in. So I've been adding simulation to this structure, which is on my big to-do list. So collect, play, replay pipeline, and the student notebooks where you can request your ARM, and then use the coachable CLI is actually more for the operational controls. And then the operational automation, I'm using a just file to sort of manage the fleet and manage the tail scale access and a variety of things. And that's actually been agentic tested, so I'll explain more of that if there's ever more time. Anyway, I'm running the MI100s, and I could be much more ambitious and go for the H100s and things. So if we look at the structure a little bit closer, I can run this on the Jetson Orin and the Raspberry Pi, and my benchmarking has shown that if I want a robot I can talk to, as well as like say pick up the red blocks or give them various tasks and challenges. The Jetson Orin would allow me to do onboard inference, where trying to do the full stack of the TalkBot, the Talk robot, plus the coachable CLI and all the other pieces here, it's really overwhelming for a Pi. So all I have to do is offload the inference, and I'm benchmarking OpenRouter versus using the MY100 or an H100, and looking at that like, hey, why don't if I use VLLM, I might be able to use multi-player, so all those different robots coming in will have a better multi-user experience on this particular thing. And every so often I bump into weird issues, but this process is being validated and working pretty well at the moment. The thing that really makes a difference is tail scale, where I have basically a management of a naming structure. So I can say this is ARM1, this is ARM2, ARM3, and I can pipe over ports over to SSL, because one of the factors is like if I do WebRTC and real-time streaming, I need to do that over an SSL channel. And there are many other things where you want a secure channel for. Tailscale makes an easy interface for that. So I just register all my devices in Tailscale, and I have access. It's super cool. The other part is a lot of my data sets are kind of going over at Hugging Face Hub, but really I can make them live anywhere. But it's a sort of a management of like publishing your project publicly, but then having all of the different places where you get your data. So if you did like a trophy artifact, back up your whole thing, you want your whole project backed up. And then mostly the pinging back and forth between the Chameleon cloud and such as inference and action controls, all of that is kind of bundled in there. So it needs a lot of, like, we talked about benchmarking and testing. There's a lot of like, how well does this work that you really have to dig into, but I have at least a platform where I can actually answer that question. Device profiles, I've been having a little bit of like, how do these things work exactly? But that's been like a little bit of a challenge. The container lifecycle, image caching, trying to provide things like, I need a new image, how do I replace that image? Will the poll do a thing? There's like lots of little things. These are not stoppable. Every so often I'll run into, can I get outbound for something? But every single one of these has a ticket that I'm getting like quick response times on. So these are kind of some bumps, but they've worked really well. I mean, I'm already so excited that I've been talking with people and they've been engaging those, and we're making progress with them. So this is just a more detailed slide, is that like Llama CPP is very performant, but if I took my whole TalkBox stack, it's like a 90-minute build time if I can, for creating the image if I do cross-compiling. But if I do it like on the bot, you get, anyway, there's a bunch of things. Vision is up and coming. So let's see, the split, remote inference. I talked about all of those. I think the thing that I like with my TalkBot project is it's a text-to-speech, LLM, tool call, and TTS stack. So you can check the performance, and I don't need my robot and all the serial ports and video to do it. I can just check the performance of the stack. It's really nice. So that's up and growing. So every time I run it, it commits to the project and I have the data. So the thing that's really cool is I can just basically request what I need to get the project done. And I just haven't been greedy enough, actually. There's so many cool things to do. And I just kind of got the pieces in place. So there are things that I put in here. We can always look. These are things like sort of some edge to cloud stuff, because I'm using Tailscale. If there was a native feature for that, I'd certainly use it, but Tailscale's working great. I have, these are just, again, small bugs. Jetson pod outbound internet, I think that's just a ticket. Persistent GPU environments, I'm still working on like how to like require those through Ansible. So I'm doing lots of operational stuff where I should be doing lots of teaching stuff. So that's my, my main goal. And then, so the way that goes here is now that that sort of is in place, the benchmarking every stage, the policy trainings that I need, autonomous policy executions will be built in. The robot agent that you're speaking to will be added, because now I can use a Jetson instead of a Pi, or I can offload that tech to another inference system and then have that capability still on a Pi. So, and then my really coup de grace will be my next generation of foo cars, which is my autonomous car project. I think will benefit quite a lot from this. So long story short is all of this has been paired with curriculum that's being built that needs to be tested. All right, thank you.
Hello, everyone. So I'm going to talk a little bit about my experiences of teaching a course that I designed this past semester in the first year of me being an assistant professor at the Illinois Institute of Technology. So before I kind of talk about the course that I designed and what its learning outcomes and objectives were, I want to first talk about my research area and research interests. So we're all kind of familiar with these vague terms that kind of describe the computing continuum as a whole. We're familiar with cloud computing, we're familiar with edge computing, we're familiar with fog computing. Sometimes these terms kind of blur together, particularly with fog, edge, mist, cloudlet, etc. But generally what can be observed with this spectrum is that there's a natural trade-off. The vast majority of data that come into the computing continuum that we use to train these large AI models that we're very interested in come from the edge, which is latent with devices that have really strict resource constraints. And on the opposite end of the spectrum, you have the cloud or HPC data centers, et cetera, which have vast amounts of compute, but relatively have very small amounts of data compared to all of the data available at the edge. So my research interests as a whole is essentially to make full use of the entire computing continuum to train, deploy, and serve AI. So rather than just focusing on building the biggest possible AI model and training it on the biggest possible machine to get the best possible accuracy, I'm interested in taking advantage of the compute, even if it's disparate across the edge and fog, in order to get the most, make the full use of the full computing continuum. And so I wanted to kind of bring these research interests into a dedicated course, which I called Decentralized Machine Learning Systems. So there were a lot of challenges going into designing this course. The first one is that I couldn't find a single analogous example out there from surveying several different academic institutions. And so I kind of had to go in with a fresh blank slate. And so I wanted this course to be very open-ended. I wanted students to be able to explore things that are interesting to them in particular. So I decided to split the course into two parts. The first part was going to be more lecture-based, where we kind of ensure that all students have a standardized common foundation to kind of explore their own interests. And then the second part of the course would focus on students pairing off into group projects and also presenting state-of-the-art research papers. And so I'm going to briefly touch on the lecture material and the focus of the first half of the course. And the first module was just to provide an overview of AI and machine learning. One of the major constraints and limitations of the course was that I couldn't really, because I had to design it so quickly, I couldn't really enforce a prerequisite and ensure that everybody came in with the requisite amount of artificial intelligence background to be able to just hit the ground running. So we first started off by kind of going over the fundamental ideas of machine learning, deep learning, what is gradient descent, backpropagation, et cetera, what are the various different neural network architectures, and whatnot. We then capped off this module by having students complete a homework assignment where they just simply had to implement, design, and then train an AI model of themselves on their own using just standard vanilla PyTorch. And then, once we completed this module, we then moved on to kind of this large amorphous computer systems module. Here, we kind of covered all of the different various forms of computing systems. So this included high performance, grid, cluster, cloud, super fog, edge computing, et cetera. And so I'm not going to go too much into details here because there was so much that we had to cover in this module, but we talked about the topological organization of high-performance computing machines, batch schedulers, different cloud computing paradigms. We also talked about the definition of edge computing, fog computing, what are the trade-offs, et cetera. And we also talked about methods in order to take apps and virtualize them or containerize them so that you can deploy them in different systems rather than just relying on the assurance that it works on your machine. And then finally, and this is the most interesting module of the course, was this decentralized machine learning systems module, where we kind of take these two areas that's more systems oriented and also more AI oriented and fuse them together. And so here we're kind of we're more so focused on discussing the state-of-the-art ways in which researchers and practitioners aim to train and serve AI in decentralized systems. And one of the key pillars of this was federated learning. And as a brief overview for those who may be unfamiliar, in federated learning, rather than taking the data that is available on edge devices and sending that data to a data center for training, we instead send the AI model to where the data naturally live. We train there, then we send the updated model parameters back to a centralized location and we average them. So the global model is essentially trained on all the data in the system without ever actually directly seeing it, right? And this has various different trade-offs in terms of model accuracy, data efficiency, et cetera. And the data challenges, the system challenges, and other challenges such as model poisoning and whatnot were things that we discussed in great length through both lecture and also through small breakout group discussions. And this module was capped off with a homework assignment, which kind of challenged the students a little bit more. And essentially what they had to do was first, they needed to simulate federated learning. So they would just do this maybe like on a laptop at their disposal. They would create a neural network. They would simulate the fleet of different edge devices. And then they would output a global model that was trained on all the devices, et cetera, using this federated learning workflow. Then they would take the global model and they would basically wrap it up in a web application. And this could be used with any type of web application framework that they would like to use, like Fast API and whatnot. And they would Dockerize this before porting this to Chameleon and spinning up a Chameleon instance where they would then host this web application so that you could actually make inference calls onto this web application in order to do image classification requests. And here is a little example of one of the student applications that they developed. And here you can see that they had trained up an AlexNet model, and they were able to send in a picture of a cat, and it correctly predicted that it was a cat. So that's the most important problem in AI. So very exciting stuff. And for the last bit, I'm going to kind of try to be mindful of time here, but we had group projects. All of the students were asked to kind of self-organize into 3 to 4 students, and they were free to use any resource available to them. The course had a course-wide Chameleon allocation, so they were free to use that and request for more SUs if they needed it. And they had to just propose an original idea that was approved by the instructor, me, and the students would essentially submit all of their code artifacts and also an 8-page report, just kind of talking about what they did, what were the challenges. And you can see that they touched on a litany of different topics, including privacy preservation of AI, gossip learning, hierarchical federated learning, LLM fine-tuning, et cetera, et cetera. So it was really cool to see all of the different interests that the students had. And now I'm going to kind of go through the challenges and insights that I learned from teaching this course. The biggest issue is that there were so many different topics that we had to discuss. And as a new faculty member, I started to realize how short a semester was. And because the course is so interdisciplinary and we had to talk about AI, we had to talk about systems and whatnot, there were so many different technologies that the students were kind of forced into learning that it became kind of, I could tell that they were suffering of a little bit of like disciplinary whiplash. So that was certainly a challenge. There was a lack of standard textbooks and materials for teaching this material. So that was a huge challenge as well. And one of the main takeaways that I've had is that for the next iteration of the course, I plan to maybe expand the lecture into just taking up the entire semester, and instead of using the group project, we would instead have like maybe more guided lab-based projects instead. So that way we can actually ensure that all of the students are using these resources in a meaningful way. Similarly, I'd like to maybe collaborate with some faculty members who might be interested in spinning up their own version of this course to see like if we can maybe learn from each other. And I'm also trying to develop a little mini textbook in hopes of kind of standardizing this course material. If interested, please reach out to me and let's talk. And also, finally, I'm going to double down on using Chameleon in future iterations of the course. The students really liked being able to use the infrastructure. That was one of the most common praises of the course. So that was really reassuring to see that the students really felt like they learned a lot from using this infrastructure in class. And so for the sake of this course, Chameleon was necessary. One of the things that I'm kind of interested in doing as well is, as somebody who uses edge computing, I'm kind of building up my own little mini edge cluster, which you can see on the right. Ignore the very brutish cabling at the moment. But I think it's important to show that these systems are physical. So being able to show like these devices are physical, it's not just a magic box in the sky. So showing students these devices in person, having them work with them in person, and before they then maybe transition into using a resource like Chia Edge would be awesome. And I think that a cool use case for Chia Edge in the future would be to, instead of simulating federated learning on like their laptops, we can instead have them deploy federated learning on multiple RPIs or Jetson modules. This is, I'm going to keep this really short just for the sake of time. The students used a litany of different services and frameworks and whatnot, including Flask, RayServe, FastAPI, PyTorch, Lightning, Scikit-learn, and fortunately, they were able to do all of these different, use all of these different tools on Chameleon, and that was really, really reassuring in terms of the usability of the platform for students. And one of the other things is hopefully in the future we'll be able to perhaps spin up some type of Slurm cluster, so when we actually talk about that in class, they can actually see what that looks like and use it practically. And I wanted to kind of end off the talk by just kind of highlighting one of the student comments, which was, quote, "One of the biggest lessons was understanding how critical a clean, bug-free pipeline is. Since a full run can take more than 30 hours, a single hidden bug could force us to restart everything. It was also my first time building such a flexible pipeline, capable of running more than 100 experiments automatically, saving checkpoints, logging metrics, generating confusion matrices, and tracking every parameter for later analysis." So I think this was a master's student, and this was the first time they had this experience, which I think is fundamental if you're going to do, novel systems research. And this was done on Chameleon, which I thought was really cool. And I hope to have more positive experiences for students in the future. And yeah, that sums up my talk. If you have questions, by all means, feel free to ask me during the panel.
Hello, everybody. Can you hear me? Great. My name is Puyan Jamshidi, and today I'm going to talk about some of our experience both in research and teaching using Chameleon Cloud. I would like to start off by thanking Chameleon Cloud people that enable us to do these experiments at a scale, spinning up over 40 distributed ML systems at the same time. Why it matters? First of all, ML system now require full stack infrastructure, as you know, and specifically for adaptive ML system, we require a lot of instrumenting the system across the stack and measuring many metrics across the stack. And this is very important to have this capability to, first of all, instrument the system as well as collecting these signals from the system. And testbed like Chameleon enable us to have enough control over these resources, and more importantly, it enabled us to do research that we can replicate even with third party, as I mentioned a little bit later, at a scale. And the goal is to really bridge the gap between research, education, and infrastructure. And today, I'm going to talk about our experience both in research, published research work, as well as teaching. I'm teaching a course called ML Systems, CSC 585. And this is a project-based course, and I'm going to highlight three student projects and kind of challenges that they faced using these resources. So I start off by explaining a little bit what we have done in these three published work. Hopefully you don't get bored. So this work is about how to autonomously reconfigure a large-scale ML pipeline at runtime. And you can think about it that we can mathematically abstract it away by specifying a multi-objective optimization with some existing constraints that we have mathematically defined for this. And this resulted into three different systems: Inf adapter, IPA, and Sponge. They have some relevance, but they have some differences in terms of a specific reconfiguration that we enable for resource adaptation. I start off with inf adapter. Quickly, I'm not going to go into detail, but basically I provide you some detail about the experiments and the complexity we require to do this research. For inf adapter, specifically we needed to spin up several model variants at the same time and be able to monitor these variants on the infrastructure and be able to reconfigure the pipeline at runtime. Specifically, we select a subset of model variant at runtime in order to provide a trade-off between accuracy and resource cost. The first insight was that the same throughput can be achieved by different computing resources, but also between swapping different model variants, as you see between ResNet 50 and ResNet 152. This is what we call model variant, to be precise. Also, we find out that we can achieve higher average accuracy if we can select a subset of these model variants, comparing with the existing solution, prior solution that was called model switching. So this is how the design looks like. We need to pull several metrics to monitor the system, and we develop an adapter basically to decide by solving that multi-objective optimization problem in order to determine what model variants we want to keep at runtime. And also we require some an actor in order to reconfigure the system. Here are some results. I'm, again, not going to go to detail, but the important thing is that we use Kubernetes. Also, we compare against Kubernetes VPA, the native autoscaler of Kubernetes, and we compare again against model switching. Also, we compared in terms of latency, and you see the real workload from Twitter that we use for evaluation of this work. Next, I move on to IPA. This is, you can think about it as an extension of this single node inf adapter. Specifically, at runtime, if you have a pipeline, ML pipeline, you see the queue size and the specific model variant that sit at every stage of this pipeline. And at runtime, we wanted to enable this reconfiguration. For example, if we wanted to add more model variants to any stage or change the size of the queue in order to sustain these external uncertainties, such as increase in terms of the demand for the system. And we have multiple different objectives, such as accuracy, latency, throughput, as well as the cost of the infrastructure that we used. And we have 3 specific parameters to tweak. Scaling means that the scaling of the cloud resources, batching, the size of the batch, and model switching, a specific subset of model variants that we want to keep at runtime for every stage. And in evaluation, we use, again, Kubernetes due to this reason, because it is a standard, and specifically it has been used in industry quite a lot. And we also used a core framework for some of these reconfiguration at runtime. We evaluated the work across different real-world pipeline, as you see, from video monitoring to audio sentiment analysis and so on. Also, I would like to highlight that thanks to Chameleon, again, this provided the opportunity that third party, specifically for this publication, be able to validate and replicate the result. We provided scripts for them in order to do this replication, which was amazing experience for us. And last thing, Sponge, which again has similarity to InfAdapter and IPA, but the difference is that here we have external source of uncertainty, which is network latency. And since network latency may cause some fluctuation, this translates to reduced time budget for some of the requests that hit the backend system. And as a solution, we enable in-place vertical scaling. This is how the system design look like, very much similar to IPA, but with some of the nuanced differences, specifically in terms of simulating this uncertainty for the network. So here are some of the results and the link to the GitHub. And for those who are interested to know our experiences, specifically in the context of Chameleon Cloud, we also have written a blog post going into the detail of experiences, if you are interested to check it out. But also, I would like to highlight some of our experience in classroom, specifically 3 projects. This is one that add a energy dimension to IPA. Basically, the students, team of students extended IPA and added this new dimension, energy consumption, which was fascinating. Also, another team have extended IPA, but now basically extended along the dimension of power efficiency with different solution. This team has developed a reinforcement learning approach. Also, another team, the third and last one, Rus AI, which basically they develop a RAG-based system, LLM system basically. And also I highlighted some of the Chameleon specific challenges that we have faced, or the students have faced in their project. So to wrap up, in terms of research, Chameleon enabled us to build this custom cluster, even like larger scale clusters, which was very useful for us and without any cost to do these experiments. Also bare metal resources and also combination of bare metal and via virtual machine deployment also enable us to spin up that complex system design and be able to monitor the system as well as reconfigure the system at runtime. Also enable us to do this auto-scaling, monitoring, and load generation. Obviously, we needed to use different tools and deploy these tools on the infrastructure. Specifically, it enabled us to have full control from operating system to orchestration of these nodes and the ML services that each system provides. In terms of classroom, one challenge was that we had many different groups using Chameleon resources at the same time. You can imagine specifically when it comes to experiments, students sometimes deploy up to 40 different systems in one day. And obviously, in terms of burst workloads, specifically near the deadline, their delivery, they face some challenges due to unavailability of resources. Some of the students have faced some infrastructure challenges in terms of debugging and some inconsistent measurement, a specific performance measurement across different nodes. So if I want to summarize, in terms of research, we had control, and these experiments have been done by PhD students. They have more experience, obviously. They face less challenges, but in education, imagine large scale system deployment, heterogeneity of these resources, and bursty workload. And obviously, like, they require some of the tooling, specifically when it comes for multi-user ML systems. So to summarize in terms of wish list for Chameleon Cloud, due to these challenges, specifically GPU heterogeneity and unstable latency as a result, bursty workloads, and some of the delays that teams have faced in terms of model loading, especially for large models, LLM-based model. Imagine that like a student needed to download the model artifact multiple times. These models are huge in terms of size. So in terms of like timing-wise, they face some challenges. And also in terms of monitoring, we used external tools and deployed on Chameleon, but like if we have like access to native observable tools, that would facilitate the experiments. Okay, I skip these. Here are summary of what we believe that might help students as well as researchers if we want to have some improvement over Chameleon Cloud resources, specifically if you have an education mode that support this bursty scheduling. Also, if we have a shared model artifact registry, especially for these large scale models, LLMs, would be amazing. Integrated observability dashboard that I mentioned, specifically when it comes to GPUs and ML pipelines, would be super useful. And if we have pre-built ML pipeline that we could reuse, that would save a lot of time. I know we have experimental management support that was mentioned earlier, but there are rooms for improvement along those line of work. And here is the last slide. So I stop here, and thank you for your attention. I'm glad to answer any questions.
So, hello, I am Freda Fund. I just wanted to get your attention, so there's nothing beyond the fun theme other than that. I'm actually not a machine learning person. My research area is wireless networks. But about 5 years ago, I started teaching intro ML just because, there was a need. We have students, they want to study machine learning. So I started teaching intro ML back in 2020. And the way we teach intro machine learning is like machine learning on easy mode, right? So we remove all the complications, we package up these nice clean data sets, we give them to students, and they train a model, and that's the end of it, right? So by design, we remove a lot of the complications because we specifically want to focus on the modeling element of machine learning. Now, personally, I also do incorporate some systems pieces in my intro ML course. So for example, I have students measure energy usage while training models with different settings. I had a little deployment project at some point. But for the most part, intro machine learning is machine learning in easy mode, right? And then after doing this for a little bit, we started to see that when students wanted to, let's say, build on that, do projects, I supervised some, let's say, independent studies. This is what it looks like when you go from there to trying to deploy real systems, right? So you go to deploy in the real world, everything gets much more complicated. There are so many pieces that no one ever taught you about in intro machine learning. And this is sort of why AI and machine learning is known for being like a project graveyard, right? It sort of has that reputation as there are these, like, I don't even know how many AI startups there are, and such a tiny fraction of them are ever going to go anywhere. And part of that is because ML seems so easy on the surface when you think of it as just a modeling problem. Like, sure, you take this data, plug it into a model, and we'll be able to do the thing we want to do, but that's really the easiest part of the whole system. So this is what we set out to address. I'll give you, the executive summary here. We proposed a course a couple of years ago. Last year was the first iteration of it on machine learning systems, engineering, and operations. And the idea is to zoom out from this, model-centric view that's that tiny little black square in the middle. This is from the classic seminal MLOps paper from 2015. And we want to learn how to build and operate these large-scale machine learning systems, which have these other parts all around it. We had a list of core topics, so we spent 1 week on each topic: machine learning systems and cloud computing, then DevOps plus ML, which is MLOps, data systems, large-scale trading, operationalizing trading, serving, evaluation and monitoring, safeguarding, commercial clouds. That left me a few weeks for little extra topics. So for example, this year my extra topics are LLM ops, RAG, and agents and MCP, because that's what students want to learn, but those are sort of secondary. And the course is designed around a sequence of hands-on lab assignments that students run on Chameleon Cloud. So there's no homework assignments besides the labs, there's no exams. It did fall down. Thank you. Okay, I'm very bad at lapel make, sorry. I'm gonna put it on my scarf. All right, that should do it. Okay, and the goal was for students to spend roughly 4 to 5 hours per week actually executing lab assignments on Chameleon Cloud. And then at the end, in those last weeks when we had those extra topics, students were working on group projects. These were not totally open-ended, so they had to incorporate specific elements from the lessons, and those had to be implemented on Chameleon. I'm going to walk you through the labs really quick. I don't have a lot of time. Okay, so they're all based around this hypothetical startup called Gourmetgram, okay, which I invented, which is an online community organized around user-uploaded photos of food. And the hypothetical is that students are graduate from NYU and get a high-paying job as an ML engineer at Gourmetgram. And so the labs follow a sequence of things they might have to do in this role. They start with onboarding, create accounts, etc. Then they sort of have a cloud computing lab where they've inherited a model from a predecessor and they have to Dockerize it and deploy it in Kubernetes. And then that involves a ton of clicks because they do it in the GUI or the OpenStack command line interface, and then they have to learn to operationalize it. They spin it up with Terraform and Ansible, and then they learn how to connect the whole pipeline end to end with Argo. After that, we look at data a little bit. So they have a new type of sort of ML feature they have to implement that involves computing real-time features and then also saving it for offline model training later. We also teach them how to use the persistent storage on Chameleon, so that's really important for what Poyan mentioned with repeated model downloads. So we teach them how to download models to Chameleon's object storage and then stream it from there for training later. After that, finally, we get to what students really want to do, which is training LLMs. So we introduce an auto-caption model for Gourmetgram, and students need to learn how to fine-tune very, very large models that don't necessarily fit in memory. You'll notice here that anytime we have lab assignments that run on GPUs, we're going to have a stack of them because we need to have a slightly different version for every GPU type. And the reason we need this is because I'm teaching 200 students at a time. And there are definitely not 200 GPUs on Chameleon at a time. So during these weeks when we're using GPU resources, first of all, we're planning in advance what GPU types we're going to use. In many cases, we have to make things available for multiple GPU types. And then my students pack in these really dense, 3-hour reservations back to back. The calendar looks crazy when we're doing this, but that's what it takes. Okay, moving on, we also look at operationalizing model training using tools like MLflow and Ray. Then we get into serving, so we look at it from the perspective of optimizing models, optimizing systems, and we also do some edge serving. And then we have some evaluation, again, looking at it offline, online, closing the feedback loop and bringing in, let's say, a human annotation platform, stuff like that. So lots of good things. So that's a quick summary of our lab assignments. I sometimes think students take classes mostly so that they can pick up keywords to put on their resume. So in this class, we give them a few dozen keywords that they can put on their resume, and that makes everyone really, really happy. Okay. What did this all end up with? So in the first instance of the class, which was last spring, we had roughly 200 students enrolled. I think the final number came in at 190. And we used, for the lab assignments only, 109,000 instance hours. So about 110,000 hours. That translates to about 500 hours per student of active instance use time. Okay, so remember I said we're packing in leases back to back in 3-hour chunks. So this is not instance time where you reserve an instance for a week and you use it intermittently. They're using it very actively during this time. We found out that if we map the resources we use to the equivalent instance types on commercial clouds, the lab assignments alone would have cost roughly $25,000 to run on a commercial cloud. It came out basically the same number on GCP or AWS, but it's very variable per student. So let's say some students spent more time on the labs and maybe repeated some of them. So the most expensive students would have cost a little over $600 probably. And all that is just for the lab assignments. So once we start bringing in the open-ended projects they did at the end, that added in another 75,000 hours of compute time, of which over 5,000 was GPU, 9 terabytes usage of block storage, and another 1.5 terabytes of object storage. At putting it all together, the entire class with 200 students would have cost roughly $50,000 to run on a commercial cloud. AWS does not give out education credits. GCP gives me $50 per student. Okay. So we also do one small lab assignment on GCP using those GCP credits, just so students have some experience using these commercial clouds too. But obviously, we would never, run anything to this extent on a commercial cloud because I don't want students to have to pay for it. There were a few things that obviously did not necessarily work well out of the box. First of all, I don't think anyone had ever done anything at the scale before. I might have been the first. Sorry, guys. So we discovered sort of a lot of issues that just came out of the very high scale and like the high density of leases. We did things like exhausting the IP address space on shared net 1 and blocking Docker pulls for all projects on Chameleons because we had so many all coming from the same IP address on shared net 1. Lots of issues like that. Also, sometimes, when there's a hardware issue or some software issue with the reservation system that needs to be resolved. So if you're a research user and you've opened a ticket and it takes 2 days to respond and resolve that ticket, that's very reasonable, right? For education use, where you have a 1-week lab assignment and 200 students packed in with back-to-back 3-hour leases, and you don't have a lot of time elasticity because we're moving on to the next lab assignment next week, that definitely caused me some gray hairs. But we got through it. We're running it again this semester, our second iteration. We again have over 110 students enrolled. We've done some things to make the labs more robust. So we've improved a few things. We added some new topics that are of interest to students. We also improved the structure of the project. So this semester, my project is students take an existing open source service and implement an ML feature inside it. So it's not like a standalone ML thing. They're doing things like taking existing, let's say Zoom clones and implementing an ML feature inside. So let's say implementing live transcripts in an open source Zoom alternative, or implementing, let's say, recipe recommendations in an open source recipe app. So this has been really neat to see, and it's going pretty well. Finally, I want to mention that all of my course materials are available online. Everything is available both as a Trovy artifact that students can click on and launch directly, but it's also all of it is through Git. So lab assignments, detailed lecture notes are all through Git, so anyone who's interested is welcome to fork it and make their own changes, do things that they need to make. Okay, I believe that's it for me. Thanks very much.
We can obviously take questions from the audience, but as the session chair, I'm going to bias this and ask the question I care about the most is, oh, no, darn it, I'm not.
Go for it.
Oh, okay.
Go for
Yeah,
it.
so I'm curious, what AI skills are you teaching? And the way that I like to think about this is, how do you prevent teaching AI skills and not the history of AI skills? I'm just curious what you all think about that. Anybody?
I have different audiences. Oh, okay. Sorry. Yeah, I have different audiences. So there's a master's of policy.
So right there.
There's the green light.
How about now? Can you hear it? We're okay, or?
He's gonna come out and give us instructions.
Yeah, we'll just use the ceiling mics for the Q&A, so you don't need to use that.
Oh, okay.
Okay, cool.
Yeah, okay. So in my case, I have different audiences, and they're being introduced at different stages. So some of them are like, you now have this new LLM thing you have to learn. So instead of sort of building people up on the machine learning portion, the Masters of Policy students are taking a concept and saying, I need to do retrieval augmented generation, or I need to do a limited number of things. So I end up focusing on what's necessary, putting the notebooks together just for those components, and scaffolding that area. Without the history of ML behind it, they're kind of just jumping into the next thing of, these are models, how do you use them? So it's, there's this bifurcation at that point.
Well, I do teach a history of ML on purpose, right? Because we're not supposed to be teaching students how to take open source software, like open source software for calling external LLMs and doing things with them. I mean, we teach some students that too, but we're an engineering school, we're supposed to be teaching engineers, and they're gonna be the ones building the next things, right? So if we weren't teaching the history of ML, then we'd end up with students who are like, oh wow, these neural networks are really cool, but what if we simplified it and they'd reinvent linear regression, right? So we teach the history of ML for a reason. That's always what computer science has been, right? There's always this tension of like, do you teach the latest and greatest, or do you teach from the foundation up, right?
Yeah.
So you have to try to, strike the right trade-off. And then part of teaching the history is teaching how we got to where we are, and why we got to where we are, and what you would use LLMs for and what you would not use LLMs for, right? Otherwise you end up with like students using LLMs for stuff that really don't need them, right? So there's a reason we teach the history of ML too.
So one of the things that I kind of notice when students would come in for office hours or to ask questions about like the homework and whatnot is students are often primed on asking, well, what's the right answer? When did this historical event happen? And I think that that type of framing is really difficult for AI, because if you have a student come in and say, well, what's the right mini batch size to train the model? There's not like a right answer. Depending on like your system resources, you might need to have a mini batch size of like 2, you might need to make it 64, it just kind of depends on what your needs are. So I would always invite students to try to explore open-ended problems. So in the first homework assignment that I mentioned in my talk, where they just have to train like a basic AI model, I would tell them the second part, you have to also come up with like an original experiment, mini experiment as I called it, and you would have students essentially come up with like a mini test where they would vary like mini batch size or learning rate and whatnot, and I left it open to them as long as they were varying something and seeing how does this impact the model performance, how does this impact runtime for the models to converge and whatnot. And I think that that was a really valuable way for students to realize that there isn't a right answer all the time, and that sometimes you do have to explore to figure out what's the best solution for your given problem.
In the course that I'm teaching, focus on the system aspect of ML systems, how specifically scalability, imagine how they, at the end of the course, hopefully they learn how to build a real-world ML system that scales, such as Google scale or Amazon scale. And students found these skills useful, specifically after they graduate and they get a high-paying job at these companies. Yeah.
Yeah, so I have questions for individual speakers, if that's okay. So Nathaniel, your federated learning course, if we had, in Chameleon, if we had capability that allows you to check out 100 or so Raspberry Pis, and maybe check them back in after you're done with the course, or keep them for the next course or whatever, would that be of interest?
That would certainly be of interest, yeah. Like, I think like one of the biggest challenges is getting students direct physical access to it. And just because like we're so close, because Illinois Tech's right down the road from Chicago, I think that would be a great opportunity to get students access to that.
So here's the thing, we actually had the hardware, and we were discussing a model where we would make that hardware available. We've got like, I don't know, maybe around 500 Pis that we can make available for classes. And we would make the hardware available, but we said, at least originally, you pay for the shipping, right? Which in your case, you're very interesting because, as you said, in your case, that wouldn't be a restriction, right? You can pick them up or we can drop them off or whatever, right? But that was, it, it's a kind of a sticking point because the last user who wanted to check out approached us to do that. He couldn't pay for shipping. And we, of course, as usual in Chameleon, are stuck in the situation where our current proposal didn't fund the things that our users want to do. So, we're kind of trying to figure out what to do it. If we pilot it and everybody wants to do it, I mean, we can do it in some cases, but, ultimately it starts adding up. And, there isn't flexibility on the funding side, right? But if we could pilot it, at least with you, or with others who, where this, sticky shipping question wouldn't be an issue, that would be awesome.
Yeah.
That would be fantastic.
Yeah.
Okay, so that, we're doing that. We're doing that like right away.
Sounds good.
Okay, and I've got other questions. Puya?
Puya, correct.
Puya, okay, it's just, so you mentioned, so multiple questions, actually. You mentioned bursty workloads in classes, but we have a mechanism in Chameleon that supports this kind of exigency, and that's advanced reservations, right? So if you know that you're going to assign something to students and they're going to have homework, you can make an advanced reservation for those resources, right? So does it not solve your, so
So you don't advertise this capability, right? But what I do for my
No, we
200,
advertise advanced reservations.
does anyone know about this capability? So for my 200 student classes, what I do is I go at the beginning of the semester and I make an advanced reservation personally under my own username for the resources I know we're gonna need in specific weeks. And then I open a help desk ticket. Did you guys know you could do this? I open a help desk ticket and the help desk converts those resources at the designated time so that they are only available on the calendar to people in my own project. They're grayed out to all other users. And then I delete my own reservations, and that frees it up for students to make reservations on those resources without having to contend with other Chameleon users. Did anyone here know that existed? Only time, because I told her.
So advanced reservations are one thing, right? And that's available for individual users.
And this is the workflow that.
What Freda is doing is not really, it's not advanced reservation, it's an advanced form of advanced reservations, okay? So advanced reservations, it's a feature that we've always had in Chameleon. We're known for this, we definitely advertise this, and it's a bit of a special sauce, right? So very few other systems support something like this, so people are typically unfamiliar with that. But yes, we do work with educational projects specifically to, and also with reproducibility projects. We work in a similar manner because they also have the same sort of bursty situation, right? But what Frida described is just a bit of a special feature that I think was kind of special for her. And I don't know, I mean, I don't think the support, what I mean by that is, I think we would have to make the support for something like this more robust if it was to be used, for everybody. But using advanced reservation with the burstiness situation, the artifact evaluation initiatives are also where it comes up. And we also deal with it by, talking to people ahead of time, and trying to support, we sort of tell them it's like a class, have your users fill out a form for what resources they need and when, right? And then we know and then we can discuss about how to support it best. So.
Is it available through the dashboard?
What?
Is it available through the
What
dashboard?
Friday described is not available through the dashboard, right?
And that workload is necessary because students themselves are extremely unreliable about doing things in advance.
I understand, but so, and maybe we need to make that an official feature, right? But right now it's available via the help desk. And it, probably, I mean, it works, they both, right, obviously. So, advanced reservations are available through the dashboard. Opening a help desk ticket is available through the dashboard, also much recommended and advertised. But, you know, I guess I guess the recommendation of the panel at this point, right, is to make this kind of feature for educational projects
Yeah.
more mainstream. Okay, so now.
Mike has comments on
Yeah.
that then.
I have maybe a quick comment on the happy path. So what Frida's doing, the reason we have this extra workflow is because the students themselves are making reservations. And so this is to make sure that they get the experience using Chameleon all the way end to end and making those reservations. If you don't have that requirement, you can just in advance go, I'm gonna make my homework 1 reservation, homework 2 reservation, homework 3 reservation as yourself for the class. And the students can use those to launch instances.
But you can't allocate who does it when.
No.
So when they all come on the last day, they can't all use your one
Right,
reservation.
right. And so this is the making your students do the right thing at the right time problem. But in the case that this meets your needs, this is available in the happy path and in the docs and in the dashboards.
But if you make the reservation, right, and you configure it for the students use the system as a shared system, which sometimes causes problems, right? So I think that what Friday is doing is probably a better approach. Okay, so that's one goes. The other question I have also for you is, you mentioned tooling for all sorts of things that I, don't remember them all right now, but monitoring.
Observability.
Yeah, among other things. So, the things that I remember that struck me, and I may not remember correctly, were things that depend very much on the individual investigators, right? So for example, the right monitoring tooling, presence of that on the instance. And we don't support that, correctly, that's right. We encourage users to support it. So the assumption, the Chameleon modus operandi is that users, if there are tools they need to install on an instance, users will install and maintain those tools on an instance, right? Chameleon's a small system operated on a shoestring, and there is a limit to how much of that operational support we can provide, right? So we manage, I don't know, 14 images at this point, or
We're down to like 9. You know,
nine images, right? So we support 9 images. We don't support 14, okay? It turns out, right? Because it takes extra operational costs to do that, right? What we do instead is encourage users to share what they did for their students, and this way, if you do something that you support for yourself, your effort is amortized, and then somebody's effort doesn't have to be spent because that is shared. And so FRIDA has been exceptionally generous to the community, and I know that people are using the classes that she packaged. Could you do that too? And do you think this is viable, or are there some things that we really should support, or are there some things that under the
Especially,
model?
are you asking about these images?
Right, for example, images that have instrumentations on them, instrumentation on them that
Absolutely.
you need
I mean,
for
for
your
the
class, right?
IPA, for example, everything is on GitHub correctly.
Yeah.
We provide
If you created Chameleon images that
Yeah.
support a certain type of curriculum, right, so support a certain kind of class, we would like to publicize this to other users, right? We would like you to write a blog on Chameleon, and we would like to maybe include that when we do tutorials. Say, look, there was this cool class that somebody's teaching, and they created materials, right? So that's kind of the approach we would take. However, if there are some things that don't fall into the, I created educational materials for my class and I would like to use that, can you tell us? What are those things?
in terms of cloud resources or in terms of education material?
No, in terms of things that are test-bed specific, rather than specific to your class, that we should still support, that we don't support currently, and we should. So for example, dealing with those bursty situations, right? We should support that, right? So we support advanced reservations, but the Friday doesn't say, this is advanced reservations for classes, this works much better, right? So this is good feedback, this is something for us, right? But something class specific, that would be something for you to maybe package for others to use. So do you have more of those bursty things or things for?
Yeah,
for support?
like we have those, yeah, definitely happy to share.
Yeah, but
If
tell
that,
us, what are they? What things that we need to support to make
like
the process
some of
easier?
the, specifically instrumentation across the stack, sometimes like we wanted to measure like energy consumption of these like
Okay, But
machines.
that's exactly the sort of thing that is specific to you, right? I mean, I
Yes.
don't know how many of those things we even could support outside of putting those tools on the image, because Chameleon is a bare metal reconfigurable thing, so once you land on that bare metal, you take control and, you know, anything that we're running there goes out, you know?
Exactly. Yeah, and
That's by design.
that's actually the need that we have, and some of the student face. They work a lot on like the resource like was deleted, and like they had to do the whole workflow from scratch. I mean, I can certainly go back and like provide a list of these needs and send it to you. But like you can think about it as mainly in the category of like instrumentation of the system across the stack, as well as like some of these monitoring capabilities, and some of the like maybe APIs in order to gain better control for like auto scaling resources. Um, Specifically, not only like bare metal, but also like some of these like FPGA, also like IoT type of devices. If we have like a capability that like give us same sort of control similar to like virtual machine and bare metal, because in the course I'm teaching, some of the students have these project, and also in my lab, the focus is on like interface between hardware, software, and like if we have these capability across different resource type, different heterogeneous type of resources, that would be amazing.
Okay. So I think that maybe, I don't know, Paul, you wanted to ask something?
Yeah, I had a comment about kind of what you're talking about, is I think one or two of you mentioned like a service that served model, like a model registry. Is something like that helpful? I mean, Freddie, you
That
mentioned
would
that
be
putting it in
amazing,
the
yes.
object store,
We've
like how does,
spin these up ourselves. So for example,
okay,
I teach students how to use persistent storage. I think that addresses a lot of your issues.
Yeah.
So like, you know, putting models in object storage solves your
Exactly.
problem, and teaching students how to stream from there. Also, the issue you mentioned of like the lease ending and everything's gone. So now that KVM has GPUs, for a lot of projects, students can do the entire thing on KVM. And that opens up a tremendous ability to use persistent block storage volumes. It's not well supported, like out of the box, like Python Chi does not support it. So you have to like teach them how to do it in OpenStack or in the GUI. But one of the earliest things we now teach students is how to bring up an instance from a persistent volume, and then, you know, whatever setup they put on it, volume's still there. When their lease ends, they just bring up a new instance. It saves so much time, also for research workflows. Like some of these research workflows on bare metal, like it takes a half hour to bring up the bare metal instance. Then it takes like another 30 minutes to like download the Docker images and download the LLMs and download all that, and then another 30 minutes to actually build your container images. If you're lucky, if there is, you know, that disk problem we had earlier this year, then it will take 2 hours to build. But you're talking like an hour and a half before you start doing anything. So moving to KVM and using the GPUs on KVM and using persistent disks cuts us all to like 1 minute. Sorry.
Did I hear a requirement for Python Chi support for persistent volumes?
Yeah, I put it in a
Yeah,
ticket once.
we do know about this.
Yeah,
I didn't understand the full
And
motivation.
there was also the issue that the default like GPU image is like 40 gig. It doesn't support any like meaningful stuff that you would want to do on a GPU. So it's almost useless for
Is 80 gigabytes better?
I don't know. By default, like I tell students, if you're, let's say, doing something on an H100 on KVM, start by creating a persistent 200 gigabyte disk. That's what we'll start with. Some students need to go up from there.
Another question, do you have capability for building like multi-GPU systems? Like,
You can
It
have
provide-
So there are like
multiple
4
nodes with
GPU
GPUs,
instances, so you can get like one node with one
Even
GPU.
like creating a memory that is shared between these.
So you
like-
can bring up like a node that has 4 GPUs attached.
Oh, okay.
That exists both in VM and in bare metal. So
Yeah.
let's say for our like large scale model training lab, we do
Yeah.
distributed training across either like 4 A100s or 4 H100s. Kate, I do have an infrastructure wish list for education in case you're
You
interested.
have an infrastructure one.
Wish list for education.
Okay, yeah, so that's my question to you. Go for it.
You want me to
Yes,
list it?
yeah.
Okay, so first of all, there is only block storage at 2 out of 3 sites.
Uh-huh.
There's only, there is only block storage at one site. I understand there are technical reasons why it can't be on bare metal. But then there is only object storage on the opposite sites. So you don't have any site that has all the types of storage.
Wait, TAC doesn't have.
KVM and TAC doesn't.
KVM doesn't
Oh,
have it
yeah,
yet.
yeah. We're working on that.
Okay,
We're
so we
working
want
on
that.
Yeah. Mhm.
There is also no like shared network across all sites, so you can use like FabNet between like Chia UC and Chia TAC, but then you can't connect it to KVM and TAC.
Working on
So
that.
now, okay, so now we have like a bunch of these like very isolated experiments where like, well, you need block storage, so you do something at Chia TAC, and then you need VMs, so you do something at KVM attack, and you need a particular like 4 A100 GPU, so you have that at Chia UC, and there's no way to connect it. That's my
Okay.
biggest wish list right now.
Yeah, plan for the next 2 quarters.
So a lot of this is on the roadmap already. One thing that I did want to ask if it would be helpful that's come up is, it's not say an image for students, but recipes for shared infrastructure for classes.
This is something that comes up a lot, yeah.
So in Friday's case, if you had the ability for just, you as the instructor could set up a Docker mirror. So your students hit that
We
instead of
have to
having.
do it because
Right.
otherwise we would block Docker polls on all of ShareNet Win.
Right.
It creates a problem for us, I'll tell you why. I mean, not for me personally, but maybe for other people who might wanna adopt this stuff. Because in order to make my class work, right, just to like work around the resource limitations of ShareNet 1, let's say. So before I start my class, I will, let's say, bring up a Docker mirror, right? And now let's say we keep running into the IP address exhaustion on ShareNet 1.
Yeah.
And the advice is to, not use ShareNet 1. So then before I spin up a class, I would need to bring up another network and put everything on that. The problem is then that all of my resources, like all of the learning materials, are pointing to the IP address of the specific Docker mirror I'm maintaining. And when my class is over, I'm not maintaining it. Someone else who wants to bring it up has to like copy everything, bring up their own, change the IP address of everything. It's very messy.
And so that, I was actually about to lead into that, which is recently I've been having some discussions offline about ways potentially to parameterize Jupyter notebooks. And I was wondering if that's something that would be helpful. I don't want to speak about how easy it would be to implement, but it does sound like a lot of these things, like I saw you making.
Not so much.
Well, I've been doing a lot more agentic workflows, so if I can parameterize the notebook, I can run it, collect the data, and then respond to like the, whatever happened when it ran. So sometimes I'll have like, one is like the student will do the request through the notebook step by step. If I could run that quickly to simulate the student action, and there was some sort of issue, I could debug it relatively quickly. And it's in an agentic loop, so it would read the error, and then I could get a response to that error, and then kind of do an iterative loop of improvement. So something like that would be pretty handy.
Yeah.
It wouldn't address the problem I described.
Because I was just trying to figure out, like, the problem is because you're having to hard code it.
Yeah, and all this stuff is not in a notebook. It's like, we're talking like Kubernetes manifests and like config files that are in repositories all over the place.
The other thing that's come up is, would stable names for things be helpful? For example, like a DNS service.
If I could get a name, like if I could bring up an instance and like have like a specific name for it. This exists on some other test beds. Like let's say on Cloud Lab, or I don't know exactly what they do now, but let's say in the Genie world, right? I could bring up an instance and like the first part of the host name was my like host name, then dot experiment name, dot site name, right? Cloud Lab has something like that too. So if I could do that, then I could hard code things like, Docker mirror dot ECE whatever dot KVM attack or whatever, and hard code that, and then it could point to different instances. That would be very helpful.
And that's why I'm using tail scale essentially, is I'm still having each of those instances self-register them in a tailnet, and I'm assigning sensible names to them. And then if I need to route to SSL or HTTPS,
right? All that built into that, in that particular product. There's a free level, which is what I'm using. So if I was doing it at some level of scale, I may not be able to keep it at a free level, but it's very capable. And anyway, it solved a big problem for me. It made things like I could look at it and it makes sense.
It wouldn't like necessarily 100% fix it, because let's say like, my materials would point to a specific like Docker mirror name. So it's still the question of like who's operating that Docker mirror.
Yeah.
Is it me? Am I operating for everyone using all the materials ever, keeping it going all the time? You can't have two people with the same name at the same time, so that won't work if it's like per class. So it doesn't completely resolve it, but it would be really neat.
Yeah.
100% of the instructions in my class are like, go to a.b.c.d, where that's the floating IP assigned to your instance.
Yeah.
So it'd be nice to not have to do that.
The other reason I brought it up is due to this performance measurement question. Depending on what you need, a recipe to set up a metric server and a log server and whatever that your class would then send stuff to would be an example of something that seems sort of well scoped to like a per class, per experiment kind of shared infrastructure.
Like Prometheus, for example.
Right, exactly. Because there's no reason it can't just run on like a separate KVM instance.
We have a bunch of like little per class infrastructure things that run on VMs like that.
So that, Rick, you essentially implemented for your class the sort of chatbot interface to the test bed.
Yeah.
that we're working on a sort of more general version of. Are you interested in collaborating on this? 'Cause we're thinking about it more from the perspective of the things that Paul and Mark were talking about. We're trying to create a more solid backend for the types of things that we want to ask a chatbot to do.
Yeah.
So, it becomes easier and more robust. But it looks like on the interface side, you have done a lot of experimentation. I think it would be good to have.
Yeah.
I mean, this is a good example of the sort of testbed type of functionality rather than class-specific functionality. I mean, we might have a smaller subset of the problems that you're solving, but the functionality itself, right, is generalizable.
Yeah, I'm trying to do it as a way to like operationally manage the class. So I'm not having to run all of them by myself. So essentially, the concept works really well, and I'd love to do more with that because like right now, like the agentic model was like getting into Zune and Blazor and getting into a lot of details, and sometimes those are not in system details. These are things that can read the system and tell me all about it, but we want to use it through Python Chi, right? So there's the command line through Python Chi. That command line could be enhanced to essentially not need the other tools.
Oh, anything you can share with us on the fine-grained level would be enormously helpful. And I'm particularly happy that you're doing that for Chi at Edge, because all that we have done so far on the configuration front is Docker containers. So and I think this is the problem to start with. It's simple enough to start with, but it's directly applicable to Chi at Edge, right? Everything else is a little bit different. So it would be a cool collaboration.
I'd be super happy because it's really cool. You can say spin up an MI100. And it starts working on it for you, and then like it's like as a human, I'm like the gopher to going to the website, pressing a few buttons, and coming back with the answer.
And did you do anything on the verification side of this? Because again, I mean, if the AI creates something that you really want for you, that's great. But if it creates something that looks like something that you really want, but
you have to. There are things you have to do to keep things kind of reasonable. And there's a bunch of guidance elements. So I have things like a lessons learned log, so that it puts in the lessons learned as it goes. It tests I run automated tests. So one of the things that's really useful is to set up what are your tests, and then the AI runs the test, because testing isn't necessarily a thinking process. It's an analyze afterwards. So then those kinds of things will help you stay in alignment with what your goals were. So if you set up, I need to bring up the number of machines.
Reflection element.
Yeah.
Of the agenda.
So there's a lot of guidance elements that that once you kind of push and pull it the right way, it kind of stays within the rules. And that's one of the elements is designing what rules will really help you the best. And that's like, a command line tool is super great because you're kind of like, it's opinionated to how you want somebody to use your thing. And if an agent's going to use it, then it has to use that tool to then stay within the behavior. Otherwise, it's looking for any tools. And any tool can be things that like the user's not supposed to use.
And do you automatically verify that?
Well, I'm right now just, verifying individually, but I can, but if you were like doing it on purpose, you'd set up a test suite to say, did it accomplish my goal? And you really have to say things like, did you accomplish the goal?
Yeah. I am through my first round of questions. We should let Ryan ask a question.
There is, and you both had your hands up
Okay.
Yes.
earlier. Go
Okay,
ahead.
yeah.
So, sorry, I got busy with other things, reframing my question. So, I've sort of run an ML ops or end-to-end system, machine learning system design course myself, and, we use some of Freda's projects. There are two things that I think are important as, academicians, so that, we want to teach students, these set of skills. But then the other question is we also want to evaluate. I find that we are doing a great job with respect to telling them, hey, follow these recipes and follow these set of steps. But when it comes to evaluating, hey, did the person learn? Which requires us to, build questions on top of this. But since this is so much experimental right now, actually evaluating them at different steps becomes challenging. So I just wanted to understand what were your experiences with respect to evaluation while running these courses, and what you think we can do in this sphere.
So I'll say, in my class, the main sort of like evaluation that's open-ended is this project, right? So we have weekly lab assignments that counts towards like a lot of the course grade, but that's basically on completion. So they have to follow the steps, take in the screenshots, and we grade that they've done it, but not necessarily that they've understood it. For the open-ended project element, it's not really completely open-ended. So we have some very specific requirements that we have specific team roles that are required. And then for each team role, we have requirements that correspond to each lesson in the class, essentially. So we're then evaluating whether they have implemented and made reasonable design decisions based on things they have learned in the class. And we have a separate rubric for each team member based on what they were required to have incorporated into their project. This semester, we introduced like a few rounds of deliverables so that if the initial design doesn't make so much sense, which happens a lot, we can give feedback and they iterate on that. So I think that has worked pretty well in terms of evaluating who is learning and then able to apply it to a new task and who is not.
Daniel, do you want to try to answer? I mean, you've just developed a brand new course. You probably thought a lot about these learning goals.
Yeah, so there was one particular challenge with regard to evaluating assignment 2, so the one where they actually had to deploy like a web application on a Chameleon cloud instance. And that was essentially ensuring that by the time the teaching assistant got to grade, that it was, able to run. And so one of the challenges there was the TA didn't have enough time to be able to do it in a timely manner, so I just kind of advised them to use their best judgment in order to see if the specification of the web application allowed them to, if it appeared as if it was deployable and they had the instructions present. So that could have been an organizational issue on my part, maybe we could have done that in a more timely manner so that maybe I was evaluating it. But I do think maybe having some evaluation-wide tool or evaluation-side tools where when students deploy an application, there's a portal where you can easily plug in some type of testing framework within Chameleon to make sure that everything kind of happens in an automated way would be very beneficial. I imagine it would be a difficult undertaking, but it would be quite a huge help for educators to be able to make sure that students
Kate, you're doing all my grading from now on.
May I just say that, maybe just having a GitLab server where students can just deployed within Chameleon
Mhm.
could be a huge help because they can then version control what they are working with.
Actually, just a comment, this is something that can be done on top of Chameleon, right, as an infrastructure. So certainly one avenue of making progress on this kind of thing would be to apply for cyber training and say, we will build this additional infrastructure on top of the system, right, for somebody to do that. But then, then there's a project that builds it and supports it and then things like that, right? I mean, it would expand the mission for us right now, if we're to provide this, we expand the mission of Chameleon without providing any extra funding. You know? So yeah, I don't know that we can do that, right? But, I mean, it's a good requirement, it's just a question of where do we put that and, just applying for another NSF project is a pretty doing.
Our
Right,
hope for that is
right.
getting students to record demo videos. Then you see they've deployed it and you tell them what to click through.
So we're at time right now. Do you want to do one quick more?
Yeah, maybe we can take one question from Manuel in the back.
So this question is to Dr. Priyan. So I just checked your paper of INF adaptive pipeline. So my question is that all the shared GPU infrastructure like Chameleon or let's say Nautilus, they all run on Kubernetes infrastructure or let's say Chameleon runs on Jupyter-based interface. So how are you calculating the objective? In the multi-objective that you have mentioned, how are you calculating the cost? Because this is a common problem on the shared GPU infrastructure when we calculate the cost, because we can't accurately measure the cost across the shared GPU infrastructure. So how are you doing that?
Very good question, thank you for asking. We basically base the cost based on the number of CPU or GPU cores, right? So it's a kind of approximation. It's not dollar amount, it's number of processing units that we spin up for the experiment, right? Basically, more technically, how many cores we allocated in order to satisfy these constraints, specifically user constraint in terms of latency, throughput, etc.
Yeah, if Chameleon could give us some evaluation metric kind of thing on this particular thing, then this would be greatly helpful for all the researchers who will be using the Chameleon infrastructure. And lastly, I have one more question.
You can find the details of it in the paper, yeah, and also on GitHub, the exact way that we measure it, and also we provided notebook also in order to replicate the results, so you can go and run them and see how we measure the cost.
So
We're going to maybe take that at lunch. It's 12 o'clock. We're over now. Thank you very much, panelists.
Thank you.